hungry and ecosystem negative activities. But the private sector has a huge amount to offer, and so we need to be, making sure we're not locking in types of financial systems that are going to continue to erode the climate and the biosphere, and there are various aspects of that. Breaking the link between deforestation and commodities is a big one. Deforestation is a huge issue. So I think that's one of the major aspects of that. But there are many other parts that we could discuss. But thanks for the question.
Brilliant. Natalie, thank you very much. We'll go on to the next speaker.
I can answer questions in the Q&A as well if people.
Oh, that's terrific.
I can see it. I can see things are popping up now. So
things are popping up.
Yeah. All right. Thank you.
That's great. So I'm going to pass the proverbial torch to Brian von Herzen, and Brian is going to talk to us about kelp. For those of you that don't know what kelp is, go onto Netflix and watch the Octopus My Teacher film. I thoroughly recommend it. It will show you the magic of this ecosystem that Brian's going to talk about. Brian, over to you.
Thank you. I hope my slides are showing okay and the audio is working all right. Thank you for joining. I'll be happy to describe marine permaculture and nature-based solutions in the oceans, which complement some of what Natalie was speaking about today. We're very happy to have the support of both Paul Hawkins' Drawdown work and also the associated film by Damon Gameau called 2040, which has really done a good job of showcasing the opportunity in the oceans as well as in the soils. So I think Natalie really resonated an important message, and that is we have to decarbonize 80% or more of our civilization. Once we've done that, there's the opportunity to regenerate ecosystems, many of which have been lost in the marine environment as well as terrestrially, and then ultimately measure the carbon export of those regenerative interventions. And so I'll describe that a bit in the marine environment. Now, the marine environment is really key because, historically, we've been getting a 30% discount on carbon. Of the roughly 1,500 gigatons of carbon that humans have emitted, roughly 500 of those gigatons are in the ocean today. Not only that, 93% of the heat captured by the greenhouse gases are in the surface layers of the oceans, which put marine ecosystems at the very front lines of climate disruption. And that means that from coral reefs to kelp forest, we're dealing with significant challenges in keeping these ecosystems alive, because oftentimes they're living within 1 degree of mortality, and thus being able to ensure their survival means being able to manage their temperatures. Now, this is a recent paper that discusses the trend of stratification in the oceans, and it's a bit of an unusual plot of the oceans. The Southern Ocean is here in the center, and it's actually the southern polar current goes right around Antarctica, and it really connects all the oceans together. We've drawn a latitudinal chart of the Pacific, the Atlantic, and the Indian Oceans, and these red colors signify the increase in stratification in recent decades, where the dark red actually represents close to 5% increase in stratification. This is important because it has a profound effect on the availability of macronutrients and the health and survival of our kelp forests, as well as our microalgae forests. And thus, it's a really important finding that the increase in stratification is here, because the biggest extinction in the history of the Earth, the Permian mass extinction, was associated with stratification of the oceans, deoxygenation, and a loss of 96% of all marine species. To avoid that, we need to really avoid those situations. And yet, I think by some estimates, we're 2 to 5% towards the Permian mass extinction repeat event, and that's a very significant situation. Some of the knock-on consequences are that we've seen a decimation of kelp forests from California to Tasmania. And in particular, these green dots here represent healthy kelp forest in 2008. Yet by 2016, we saw a loss of 90% of that kelp forest due to the big warm blob, El Nino, and quite frankly, climate warming that we've seen on a global scale. So it's a significant problem and one that we need to address fundamentally. At the same time, in the Western Pacific, we've seen decreases in seaweed farm operations from Indonesia to the Philippines, where something like 60% losses were experienced in 2016, and half of the seaweed farms were abandoned in parts of Indonesia. Similar problems in the Philippines. And so it has a significant impact on the 250,000 seaweed farmers in the Philippines and 2 million seaweed farmers in Indonesia, who are subsistence seaweed farmers living on the front lines of climate disruption. Thus, it's a key opportunity to try to address that. Similarly, for every 1 degree increase in temperature means that we have roughly 5% less marine biomass. This is latitudinally averaged. And so that in the tropics in particular, we're seeing a multiple of that in terms of decrease. And that means that starting in the tropics and the subtropics, but also seasonally in temperate latitudes, we're seeing a decrease in marine biomass with the increases in temperature. And these have profound effects on our marine ecosystems. Similarly, when we look at the carbon flux ratios, realize that in order to stay anywhere close to 1.5 degrees Celsius, we're going to have to look at not only decarbonizing our civilization, but secondly, looking at effective ways of drawing down. And the potential for marine drawdown is similar in magnitude to the terrestrial drawdown that Natalie discussed. It could approach ultimately similar numbers of gigatons that can be done in terrestrial ecosystems. We like to say once if by land and twice if by sea. And that's one reason we've dedicated a lot of our work in recent years to the marine environment, because it's one that's less studied and less well understood, but it's one that has at least perhaps as large potential as the regeneration of terrestrial ecosystem services. This gives you just an amazing feeling from my perspective of the mass of dissolved inorganic carbon, and that is carbon dioxide, dissolved in the middle and deep ocean today. And it's truly enormous compared to the atmosphere, which is the black box of 860 gigatons of carbon. We have 38,000 gigatons of carbon in the middle of deep ocean and room for plenty more. And so the problem of carbon in the ocean is not one of the total amount, but one of distribution. And the biological pump does an excellent job of taking carbon out of the surface layers of the ocean and put it into the middle and deep ocean. That also decreases ocean acidification. It's noted that the ocean acidification levels within and downstream of a kelp forest are substantially lower than they are within other parts of the ocean. And thus, the deep ocean represents a vast potential for a blue carbon sink that can be sustained for centuries, if not longer. I like to call this picture Planet Ocean. I'm talking to you from our overseas headquarters in Queensland, Australia, on the left side of this image. And my home state of California is on the other side on the right. And between the two, there's roughly 100 million square kilometers of accessible ocean area. And according to David Attenborough's documentary, it's mostly empty ocean. And that mostly empty ocean can be harnessed to effectively enable the regeneration of kelp forest ecosystem services offshore in regions that have kelp forests, and tropical seaweeds in regions that have tropical seaweeds. The approach I'm going to describe for you, marine permaculture, is amenable to a wide variety. It's a platform for a large fraction of the 14,000 species of red, green, and brown seaweeds and brown kelps that are available. And of course, the deep ocean stores a vastly larger amount of carbon than the entire atmosphere. Similarly, what is very surprising is that this algae bed and reef plot down here at the bottom shows that we can store up to 15%, actually flex, we can capture 15% more carbon per square meter per year than even at the Amazon rainforest. And so if we take this highly productive kelp forest and seaweed forest and deploy them in a very small fraction of the open ocean regions, we can in fact have a very large multiplier on the potential primary production that's available to regenerate these ecosystem services initially. Several thousand square kilometers of kelp have been lost already, and then ultimately to increase those over time. Now, there's been work done by a number of authors that discuss the macroalgae forests and the carbon sequestration that occurs naturally. Perhaps 11 to 30% of it does get buried in sediments, but the roughly 2/3 of it, in fact, of the seaweed that does reach the deep sea gets remineralized either by microbes or by macrofauna, and they're remineralized to carbon dioxide. And that deep ocean carbon dioxide then is carried by the deep waters with travel times that can be measured in centuries. These are the few of the locations where deep seaweeds have been discovered at depths of 1,000 to 2,000 meters. And these locations have both brown, red, and green seaweeds that have been discovered in these deep water locations. In particular, we've noted that back in the 1800s, pre-industrially, there were continuous rivers of kelp off the California coastline, extending from Central California to Mexico. And today, it's a tiny percentage of what once was. So it's one that's really significant. Now, marine permaculture is an approach where we restore natural upwelling that's been lost due to climate warming. We can irrigate a kelp forest and regenerate this ecosystem that ends up not only growing kelp and the invertebrates that live in kelp forests, but also regenerates fish habitat that is a key to regenerating sardine populations and other forage fishes. So we see this as a really key opportunity. Before global warming, and offshore wind would provide plenty of upwelling to the surface with associated macronutrients, including nitrate and phosphate, being provided to these kelp forests. In a global warming world, the thermocline is deeper, the temperatures are warmer, and it prevents upwelling from occurring at the normal rate. That is a physical barrier, energy barrier, to actually restoring that overturning circulation. But with marine permaculture, we're able to utilize solar, wind, and wave energy to irrigate up to a square kilometer of kelp forest offshore and restore the regional ecosystem services offshore, far enough offshore that they don't impact the coastal environment. And so this is the general approach that we've been using, and we envision both hectare scale and multi-hectare scale marine permacultures in the future that can regenerate kelp forest in tropical to temperate latitudes. And in the tropics, we can use local red seaweeds to do similar accomplishments. These can be partially harvested, perhaps every 90 days, and they can produce food, feed, and fertilizer products. And those products that are not used directly for food, feed, and fertilizer, the residual seaweed, can be sunk to the middle and deep ocean. And we see that as an opportunity to provide a carbon negative and climate positive solution at the same time that we're actually regenerating ecosystem habitat and also providing food, feed, and fertilizer products that are highly essential. The per square kilometer, we're estimating 3,000 tons of seaweed, potentially several hundred tons of fish, and over $1 million in revenues. And ultimately, this fixes approximately 3,000 tons of carbon dioxide per square kilometer per year as well. And so we see the opportunity to sink the residual carbon that's not being used for food, feed, and fertilizer. We can track that sinking past 300 and 1,000 meters. And the event horizon or sequestration horizon is approximately 100 years at 300 meters and perhaps close to 1,000 years below the 1,000-meter depth horizon. So we see that as a key opportunity. And in fact, the carbon to phosphorus ratios indicate that for every upwelled mole of phosphorus, we're sinking several moles of carbon as a result going down. And so these ratios are really substantial for macroalgae, where they have higher carbon to phosphorus ratios, and thus that provides a net benefit to the sequestration for microalgae. We can measure that sinking using a variety of sediment traps that have been established over the past several decades with standard operating procedures. And this illustrates how the deeper we sink the carbon and in the form of seaweed, the longer the sequestration time. And that can be verified by maps such as this, which provides radiocarbon dates of the deep water that provides very accurate maps of the number of centuries of sequestration that's possible. And from this, we can calculate the median time to outcropping of abyssal waters and thus the sequestration time. Past 100 years, the United Nations is prone to give carbon credits. And we see even RPE Mariner has indicated that if this is deployed with several 100,000 units, more than 100,000 units, that potentially a gigaton or more of carbon can be captured at the same time that we can generate agricultural products and increase food security and ecosystem life support. So far, we've developed not only the theoretical framework, but also deployed experiments demonstrating that algae would grow with upwelling, and that this trough-based systems demonstrated the commercial growth of, or the growth of commercially relevant seaweeds under deep water irrigation. We're now working to expand in several stages to a hectare scale. And once that's proven, we should be able to build sustainable industries from Australia to the Philippines to the Mediterranean, potentially, of being able to build and grow sustainable hectares of seaweed and be able to enable those to thrive for years to come, and then ultimately consider going to larger scales. We have, with thermal imaging, demonstrated that cooler water can grow the seaweed. These darker colors are much more productive seaweed compared to the light colors on the right side. And that's produced really substantial growth curves where we're seeing a significant doubling of the weight of the seaweed with deep water irrigation compared to controls that actually lost weight during the same months of the year. And so we see this as a great opportunity both in the tropics and in the temperate regions. We saw 4 times the growth of these mature kelps in higher nutrient zones relative to baseline control kelps. And so we're very encouraged both by our temperate and by our tropical results. So from that perspective, we see that as a key opportunity. This is a short simulation of a 10th hectare scale model of a marine permaculture platform. And it uses solar power, marine solar, to actually do the deep water irrigation. And the seaweeds are located in the outer ring, where you can see some of the radial lines extending and supporting tropical seaweeds in this case, but also temperate kelps could be supported as well. These platforms we see as being scalable and really leveraging a lot of the infrastructure of traditional salmon aquaculture that has been proven to work effectively in seas of up to 10 meters. So we believe this would be highly effective offshore and highly resilient to storms and other challenges that occur from time to time. These renewable energy pumping systems can bring water up from the deep and restore the natural upwelling that existed pre-industrially, and furthermore can provide a sustainable supply of nutrients and overturning circulation that's required for these ecosystems to do well and to thrive. Once these smaller systems have been demonstrated, we believe that commercial hectare scale systems can be deployed, and we're looking forward to assist with that industry. I'm going to try to progress this. So we've summarized the amount of seaweed that we can sink, and the fish harvested, and the carbon that can be sequestered. And with that, I thank you for your attention and look forward to your questions perhaps later in the session.